Our cube robot uses 3 cold gas thrusters for translational motion. These were selected for their high level of precision and compactness. Furthermore, they're also highly reliable and simple to operate. For rotational motion, we chose to use 3 magnetorquers, which allow for the satellite to be rotated either direction around an axis with a simple electrical current. It also increases the fuel economy because it doesn't rely on the fuel of the thrusters. These components together allow for 6 degrees of freedom in movement. It also has a highly modular design, with each part being easily removable, exchangeable, fixable, or modifiable. This opens the design to the use of commercial off-the-shelf part usage, or COTS part usage. Each cold gas thruster has their own fuel tank attached, shown here. And we also implemented a choked converging and diverging nozzle on the thruster to accelerate the gas out of the thruster at a higher speed, which increases thrust per unit mass of fuel expended. And this is the nozzle shown here. The magnetorquer assembly consists of the magnetorquer, the aluminum mounts, and the carbon fiber pipe clamp. Aluminum mounts were chosen for vibrational resistance, and carbon fiber pipe clamp was chosen because it comes in direct contact with the magnetorquer, so a non-conductive material is needed to prevent it from interfering with the induced magnetic field and current of the magnetorquer. Here's the assembly of the robot. As you can see, one thruster is mounted parallel to the X, Y, and Z axes of the cube satellite, or based on the presentation screen. One is vertical to the screen, horizontal to the screen, and into the screen, for translational maneuverability in all principal axes. Likewise, one magnetorquer is mounted parallel to the X, Y, and Z axes of the cube satellite for rotational maneuverability around all directions. The magnetorquers are mounted onto panels, which can be seen on the internal view. This is the panel, which can also be seen here on the isometric internal view. These panels are connected to the robot via bolted rods, which run through the frame of the assembly right here. In the isometric views, the frame can also be seen to have a screw and joint design on the walls, where these are the joints and these are the screws. These walls are then connected with these screws and joints to make up the entire frame. The robot has a skeleton body, which means there's no body panels outside of the frame. This makes the maintenance and operation easier and has no significant effect on the dynamics, especially when operating in a zero-gravity vacuum.
In concept, the magnetorquers create a magnetic dipole, which interacts with the Earth's magnetic field to induce a moment. Below is the full derivation for the 3-dimensional equations of translation and rotation. The first equation describes how the magnetorquer magnetic dipole is produced, with the dipole being proportional to the number of loops, the amount of current, and the cross-sectional area of the wire. Equation 2 shows how torque is produced from the cross product of the magnetic field. Equation 3 shows that the moment of inertia used is a scalar quantity due to the nature of 2D rotation. Below, equations 4 to 7 describe angular acceleration as a function of current, which is our control variable. 4 relates 2-dimensional torque to angular acceleration. 5 substitutes torque with a magnetic dipole crossed by the Earth's magnetic field, and 6 rearranges to solve for angular acceleration, while 7 rewrites the satellite's magnetic dipole in terms of current, factoring out the relevant scalars. As the thrusters are collinear with the center of mass of the robot, translational motion is the exact same as the Astrobee. This derivation is a proof expressing that gyroscopic coupling is impossible with magnetorquers for 3D rotation. We will not be going into this due to the limited amount of time we have.
Okay, now we'll be moving into our simulations. For the various initial conditions, the robot's going to be attempting to follow a path of y equals x of t and adjusting based on the initial conditions. I'll play them. In this first one, it starts close to 0 on the origin in the spatial plane that we're in. with a positive x velocity and adjusts its y force to attempt to follow the path. The second one starts above the line, approximately 10 units from where it's trying to be in the path, with a negative y velocity, and adjusts its force to a greater degree to try to follow this path. The second one is just going to start slightly above the intended path, about 1 unit above, with a low but positive x velocity. And you'll notice that all of these, the x force and x with time is constant at 0, because it does not need to, if it starts with an x velocity, it does not need to increase it to follow this path with time. And the x, you'll notice the x velocity is constant from these position graphs, and you'll notice the trajectory error just kind of oscillates as the controller attempts to rotate the robot to position its thrusters in a way to follow the path. You'll notice this torque also oscillates constantly as it does this frequently, and the controller continues to miss the path but attempt to get back on. Now we'll be moving on to our object avoidance. Just about this, as it follows the same path but with an object in its way that it needs to avoid. You'll notice the x velocity is no longer constant, and the x force has a sharp spike at the time, which is about 5, where it interacts with the object and goes around it and then follows the intended path again. You'll notice the trajectory error no longer oscillates, but has a specific double sine wave jump at the time where it's interacting with this, as it tries to push away and becomes further away from its intended trajectory, while eventually returning back to it with this oscillation point down here. The force in the x time also shows this change, as it has, once again, at the about where the time of interaction with the object occurs, the force in the x and y both show the thrusters activating to push away from the cube, from the object. Our chosen path, we chose a circular path, and you'll notice the x and y position as well as x and y velocities just oscillate with time, and the torque and roll versus time oscillate, as well as the robot has to constantly adjust its torque and angular velocity and angular position to allow its thrusters, as it only has them on 3 sides, to keep it following along the path. Something else you'll notice is the trajectory error no longer oscillates with time, as it tries as the PID controller is able to follow a circular path over time much better than it was able to follow the solid. This also corresponds to the x force versus time, as it slowly approaches a constant 0 value.
During the simulation, it was observed that our magnetorquers provided too little torque, which results in slow rotational motion. We also found that the robot was imprecise when conducting corner turning, particularly when making wide corner turns. As a result, the following potential improvements were proposed. First is direct torque increases, which include using reaction wheels instead of magnetorquers, or using gyros, or using just more magnetorquers. Furthermore, we proposed the use of gimbaled and variable flow nozzles, which would allow for the use of thrusters to contribute when making significant rotational motions, especially if used at the same time as translational movements. However, this also would significantly increase the complexity of programming the movement of the robot. We also proposed the use of 6 thrusters, with 1 on each side of the robot for translational movement, so that the robot doesn't need to rotate completely just to fly in a different direction. There were also improvements suggested to improve the mass distribution of the robot. This includes full internal mounting of all the components inside of the robot's frame, which increases compactness as well. Furthermore, we proposed implementing counterweights to centralize the center of mass of the robot, as well as a centralized fuel system to connect all the thrusters, which would also prevent changing the mass distribution as the robot expends fuel.